All right, we're going to do cell potential now, which are the numbers that he was talking about with that E on his video from last night. So this is on the back side of your notes. It starts with why do electrons flow spontaneously. So in your video with him, essentially you saw a reaction taking place when the reactants never even touched each other, which is just crazy and fantastic and wonderful. And it's the whole reason why batteries work and things like that, because it allows you to control when the reaction is going to take place. If we plop some, zinc into some copper 2 sulfate, you can't stop it from happening once you've started it. With this, you can stop it by taking out that salt bridge or disconnecting the wire between the two. So it's fascinating. I think it's just exciting. But so this is going to allow us to determine if we have two parts of our cell and we connect it, will the electrons flow spontaneously, or which direction will they flow? So this will help us identify what's happening at the anode and what's happening at the cathode, decide what's going to be reduced and what's going to be oxidized. There's all sorts of nifty things can come out of this. Out on your desk, you should also have your cell potential, you should have your notes on cell potential, and then you should also have your standard reduction potential table, that table with all those numbers and equations that I gave you along with your notes. So go ahead and have that sitting out on your desk. So the first question you see on your paper is, why do electrons flow spontaneously? Well, they flow from the cathode to the anode because of a difference in potential energy. Just like see this picture of a waterfall. Water flows from the top of the waterfall to the bottom because of a difference in potential energy. So the way a cell is set up, the cathode and the anode, it's going to want to go to, I'm sorry, I'm saying this wrong. So if the potential energy of the electrons is higher at the anode than the cathode, then those electrons are going to flow spontaneously in that direction. Okay, so they'll always flow from the anode to the cathode. And if you think about that, that makes sense, because we said, remember, red cat and anox, right? So we said reduction happens at the cathode and oxidation happens at the anode. So you're saying they're going from the anode to the cathode, which anode is where you're losing electrons, and cathode is where you're gaining them. So that should always be a logical connection that you should be able to make. All right, so cell potential, and this was what he was calculating when he was doing that E. They call it a bunch of different things. Most of the time it's called E cell, okay, or EMF, or voltage a lot of times, just the cell voltage, okay, it can be called as well. But this, if you see, is the difference between the potential energies. So those voltages are measuring the difference between the electrodes in the cathode and the anode. Now, this is super important, and just these two bullets alone can answer a number of questions that'll be asked on the AP test. If your E cell is positive, then that means your reaction is spontaneous. So kind of like back when we did equilibrium constant, and we said if the equilibrium constant was greater than 1, that it was spontaneous. Well, it's the same thing here. If you know that your E cell is positive, then you know the reaction is spontaneous. If you set up a cell that has a negative value for its E cell, so hypothetically you say, well, what would this one work, and you set it up, then it will be non-spontaneous. It will not have those electrons flow. All right, so you have to be able to set them up correctly, which you're going to learn how to do today. So if the E cell is positive, it's spontaneous. If the E cell is negative, it's not spontaneous. You may pause and write that up at the top of your paper, just sort of in big letters, just to get that fact down, because that's a very important piece of information. All right, so these are the three things that cell potential depends on. It depends on what's inside the beakers and what type of electrode piece of metal you have sticking in your beakers. It depends on the concentration of the reactants in the products, and it depends on the temperature. Okay, so all three of those factors are important. We're going to get into tomorrow some changing of some of those factors as well. Okay, for today's work though, we will be working only under what we call standard conditions. Standard conditions for redox stuff is 25 degrees Celsius and 1 molar solutions. Again, we can do this when it's not 1 molar solutions, but in order to be able to use that table that you have in front of you, you notice it says standard. So this is at 25 degrees Celsius and 1 molar solutions. By the the way, that table that you have with all the reduction potentials on it, that is one of your givens on the AP test. It'll be in your reference packet for the free response, not for the multiple choice. In the multiple choice, they'll give you what you need within the problem. So you do not have to memorize those values at all. All right, so this right here, standard reduction potential, is what's on your table. You look up at the top of your table, that's what this is a table of. Standard reduction potentials really are just telling you the likelihood of something to be reduced. It's telling you how likely that substance is to be reduced, okay? And that is useful because if you're comparing two things on that table and you know one of them is more likely to be reduced than the other, then you know which one's going to be reduced. If you take a look at your table, oh, hold on, I got one. Look at your table, I'll show you what I mean. They're all written as reductions, but you can look at them in the reverse direction, okay, as oxidation as well. But if you go through, go ahead and find, I don't know, I2. Okay, go down the list about 10 or 12, you'll see I2. It has an E reduction value of 0.53. Go all the way down to the very bottom, say lithium. Its reduction potential value is negative 3.05. So the fact that I2 has a higher reduction potential, okay, a more positive value for its reduction potential, means that it's more likely to be reduced. So if you put those two in a reaction together, I2 is the one that's going to be reduced, and Li plus is the one that's going to be oxidized. So, and we're going to do that more in a second. We'll write it down in our notes, but it can be really, really, make it very, very easy to tell what's going to be reduced and what's going to be oxidized, okay? And like it says here, we're going to use these reduction potentials to ultimately calculate E cell, which is what he was doing in his PowerPoint, okay? So here's the equation. The E cell, and notice the little degree, just means that we're under standard conditions. Okay, the E cell, so the overall voltage that will pass through that wire is based on the reduction potential of what's at the cathode minus the reduction potential of what's at the anode. So remember, what's at the cathode is the one being reduced, and the one that's at the anode is the one being oxidized. So you're going to have to know which one's being oxidized and which one's being reduced, and then you'll look up their values on that table, and you'll simply subtract them. Reduced minus oxidized. Notice right here, no coefficients. Coefficients do not change reduction potentials. Reduction potential is purely based on the element itself, not how it's combining with other elements. Okay, so it's only about what that individual element's charge is changing. So no coefficients. So we don't multiply or anything like that. And then, like this bullet says, they're either going to be given to you in the problem for a multiple choice, or if you're in the free response section, you're going to have the chart to look them up for yourself. Okay, and I'll show you how these work. We're going to do a kind of a bunch of different types of problems because there's a lot of different things that can come out of this. So this first one says, using the data from the table of standard reduction potentials, calculate the standard EMF, the E cell, for a cell that employs the following overall reaction. So you have aluminum reacting with I2 to make Al plus 3 and I minus 1. So what we need to know, so we can set up our equation, because our equation is E cell equals the reduction potential, so E red, that's what E red is, reduction potential, for the one at the cathode, which is the one being reduced, minus E red of the one being oxidized. I like to do it in terms of one being reduced minus oxidized instead of saying cathode minus anode, because that's more information that I would have to then deduce. So we need to know what's being oxidized and what's being reduced. Up until now, if I gave you this equation and asked you what was being oxidized and what was being reduced, you would look at your oxidation numbers. So let's do that. Aluminum has an oxidation number of 0. I2 has an oxidation number of 0. Remember, coefficients don't matter. Al plus 3 has an oxidation number of plus 3. And I minus 1 has an oxidation number of minus 1. So aluminum is going from 0 to plus 3. That means it lost electrons, so it is being oxidized. I2 is going from 0 to minus 1. That means it gained electrons, so it is being reduced. Okay, so I now know which one's which. I'm going to do iodine for this one, and I'm going to do aluminum for this one. Now, on the paper that you have with all your reduction potentials, the equation may not look exactly the same, okay, and I'll show you what I mean by that. Let's look at your table. Let's find I2 first. We were just looking at I2, so you'll know where that one is, about 10 or 12 down. That one is written in the same direction. You see I2 is making I minus, and if you read that value, it is 0.53. So we know that the one being reduced is 0.53. Okay, so we'll go like that. Now I need to subtract the one being oxidized. So when I look at my table for aluminum, you'll see that you actually, on the left side, the leftmost side, you find Al plus 3. It's about 10 up from the bottom. Now the equation we has the solid one on the reactant side. This one has it on the product side, and that's because this paper is showing it to us as a reduction. But in this problem, it's being oxidized. But the great news is the way that this equation is written, you don't have to worry about that. You just find the one on your paper that has Al and Al plus 3, and you write that value down. This minus sign right here will take care of the fact that it's actually the opposite of what the paper is showing. Okay, so you just have to literally find them on the paper. So aluminum is negative 1.66. And then we simply just subtract, and we end up with our value of 2.19 volts. So if you're given an equation, figure out which one's being oxidized and reduced. Do the reduced minus the oxidized, or in other words, the cathode minus the anode. Look up the values off the table, and then subtract them. And the unit will always be volts. So that's one type of problem that we will see. All right, oops, skipped. All right, so you've got this table. Again, this is a picture of what you have in front of you. And this general rule is super important because they're going to ask you just sort of like hypothetical type questions too, not just calculation ones. And this says the more positive the ERED value, the greater the tendency for that half reaction to be reduced. That's what I was saying before. So if you look at yours, I actually wrote it already for you, that these ones up here are most likely to be reduced, and these ones are most likely to be oxidized. And again, it just comes from the fact that these ones are more positive in their ERED values, these ones are more negative. And by the way, don't forget, if they're more likely to be reduced, then that means they would be good oxidizing agents, right? Because that's the opposite. And if these ones down here are being oxidized, then they would be good reducing agents. Now, I have that written on your table, but please realize when you get to the AP test, that will not be written on your table. So you can always start when you start your test by doing that, you know, just to kind of give yourself a little reminder. All right, so how could we use that? Well, here you go. I just wrote that by hand, and it's right there. Okay, so you have that down now. These here on this slide are some common oxidizing agents and reducing agents. So again, oxidizing agents are things that are most likely to be reduced. So you'll find these ones have more positive ERED values. It doesn't have to be positive, but more positive. And then these ones are reducing agents, so they're the ones that are oxidized. So they're going to have the more negative ERED values, the reduction potential values. Okay, so sometimes they ask questions about those types of things, so you can kind of just look at your table. This makes sense. If you look at the reducing agents, those are things that are more likely to lose electrons. It's metals and your H2, which we know want to lose electrons. All right, so here's another practice problem. This is a very common type of problem that we will see on the test. This is very common on the free response section. So they'll tell you have a voltaic cell, and these are going to be the two reactions. But notice they're both written as reductions. Okay, you can't have a reduction and a reduction. One of these should actually be flipped. One of these is going to actually be an oxidation. So it's our job to figure out which one will be oxidized and which one will be reduced. So we're going to look up their reduction potentials for both of them. And those reduction potentials are going to allow us to figure out which one really will be reduced. So if you look up cadmium, make sure you find the right cadmium with the right charge. The reduction potential value is negative 0.4 volts. And for Sn plus 2, the reduction potential value is negative 0.14 volts. So the one that is more positive is the one that will be reduced. The one that is more positive. Now they're both negative, but one is more positive than the other. So this one here is more positive. So this is the one that is going to be reduced. Therefore, this one is the one that is going to be oxidized. So the question asks us determine which reaction is happening at the anode and which one's happening at the cathode. We know oxidation happens at the anode, right? Oxidation happens at the anode. and ox was our little mnemonic device. So let's flip this reaction so we can say that cadmium is becoming Cd plus 2 electrons. I flipped it because remember it's losing electrons, so it'd have to be shown that way. And then at the cathode would be the one that's being reduced. That would be our Sn plus 2. So Sn plus 2 gaining electrons to make Sn solid. So look up your values. Whichever one has a more positive value is the one being reduced. All right, another type of problem. Which of the following species is the strongest oxidizing agent? Strongest oxidizing agent means most likely to be reduced. Okay, so we're going to look up reduction potentials. Find silver, Ag+, on your table, and you will see that it has a voltage of 0.8. You look up chlorine, it has a voltage of 1.36. You look up Mn plus 2, it has a voltage of negative 1.18. So the one with the most positive would be the most likely to be reduced, and therefore would be the strongest oxidizing agent. Plus on our list, halogens were listed as good oxidizing agents. So you also could have gone that direction, but this way is very straightforward if you have the numbers to look at. And that's that type. Then we have this one. This one, it wants us to use the reduction potentials to figure out whether the reaction is spontaneous under standard conditions. So in other words, it wants to know if E cell is positive. If it's positive, it's spontaneous. If it's negative, it's not. So we're going to go through our problems kind of like we did before. We know the oxidation number of copper is 0, and it goes to a plus 2. So if it goes from 0 to plus 2, that means that it lost electrons, so it is being oxidized. Hydrogen goes from a plus 1 to a 0. If you go from plus 1 to 0, then you gained electrons. So it is being reduced. Okay, so now I know my reduced and my oxidized. So my E cell, and this is standard conditions, is going to be the reduction potential of the one being reduced minus the reduction potential of the one being oxidized. Okay, so E cell, reduced one first. So the reduced one is the H+. So you find H+ on there, you'll see that its reduction potential is 0. The reason why it's 0, just for a quick little interlude, is because it was the basis for the comparison for all the others. When they determined all the other ones, they used that one as the baseline. So it is 0. And then the reduction potential of the one being oxidized is copper's. So if you look up copper, make sure you look up the copper with plus 2. There's a copper plus 1 and a copper plus 2. You want the one that's plus 2. Its value is 0.34. So when you subtract these, you get 0.34 volts. That is negative cell potential, so that is non-spontaneous. So if you set this cell up this way, it will not flow electrons from the anode to the cathode. Okay. Second one, we have oxidation number of 0 going to a -1, so that is gaining electrons, so that is being reduced. We have an oxidation number of a -1 going to a 0. So that lost electrons, so that is being oxidized. So again, we want to do our reduced one minus our oxidized one. So our reduced one is chlorine. So chlorine's value on the table is 1.36. Minus our oxidized one, which is iodine. We look up iodine and its value is 0.53. Calculate your cell potential. Comes out to be 0.83 volts. So the answer to this one is that it is spontaneous. All right, so lots of things you can do with this. Make sure you know your spontaneous is positive cell potentials. So if once you've used the numbers from the table and subtracted, if it comes out positive, it's spontaneous. The table numbers don't tell you spontaneous or not because they're only looking at a half reaction. They're only looking at half the situation. Also, looking at your table, make sure you know the ones at the top, the more positive ones, are more likely to be reduced. The ones at the bottom are less likely to be reduced, therefore are probably the ones that are going to be oxidized. All right, send me an email because I love getting 80 emails that has what you learned, something important that you learned, something that you have a question on, and lastly, I should think of these before I start to record, shouldn't I? I really liked your food choices, by the way. Those were good. Oh, I don't know. Tell me a joke. There we go. All right. I will